In this video, we're going to talk about neutral conditions. So this is when we're taking a pi electrophile and we're just treating it with its nucleophile. And this case, we don't see any H2SO4, we don't see anything like NaOH, so we don't have a strong acid or a strong base. So we're under our neutral conditions. We can identify our pi electrophile. That's the one with the carbon that's doubly bound to the oxygen. So this one here is our pi electrophile. And the E plus is short for electrophile. And then our nucleophile is over here. And with these ones, it's also important to know a lot of the times that pi electrophile is going to be on the left-hand side of the arrow, but it doesn't necessarily have to be. We could kind of show that anywhere, and that's why we don't want to get too stuck on what position the molecules are in terms of how they're drawn in the reaction itself. We want to think about those function groups that the molecules have. And so that carbon of the carbonyl is what we're going off of because it could be written over top of the arrow, and this one could have been over here, especially if it's a larger nitrogen group. And so you always want to be looking for the carbonyl itself, and that's going to be your pi electrophile no matter where it's written, and then your nucleophile is going to be the other component. And so for this mechanism, it's actually shorter than the acidic conditions because now we don't have to worry about protonating first and doing a lot of these proton transfers. It's going to be a proton transfer, but that's it. And so, under the neutral conditions in the introductory video for the conditions, we did talk about how with neutral conditions we can just go straight to the attack. And so that's what's going to happen here. We're going to do our nucleophilic attack to make our tetrahedral intermediate first, because we don't have a strong acid to protonate, so we don't have to worry about that. That's going to make our tetrahedral intermediate. The nitrogen is going to come in with its 3 H's still attached. So that's going to mean that it's positive. We're still going to have our chlorine. And we're going to make an O minus, but that's okay because we are under neutral conditions, so we can make that pretty strong base there. What we're going to do now is same thing we did right after the nucleophile attack in the acidic conditions. We do want to make sure that we're alleviating that charge on the nucleophile. It comes in and it's positively charged. We can remove that. We can use another molecule of NH3. It's noted that it is in excess, so we can alleviate that charge or do that proton transfer off. To get this molecule here, which will be NH2 with a lone pair, and then the oxygen is going to stay the same, and then the chlorine. So we're going to alleviate that charge there. And one thing you might be wondering is how come that oxygen just doesn't come and take it? One of the problems with doing intramolecular proton transfers like that is that there'd only be 4 members, and 4-membered ring transition states aren't always very stable, and so it's so much more likely for another molecule of this to be floating around to be able to go and take that H. And so that's why we don't show it intramolecularly. So don't show it that way. Something else will come and remove that proton. So now we have our tetrahedral intermediate still. What we're trying to do, we have to think about what are we trying to do overall in that reaction. We always want to replace this group that's attached to the carbon of the carbonyl with whatever our nucleophile is. And so we've got our nucleophile on there. Now we have to get this group off. Because we're not in acidic conditions, we don't have to worry about transferring any protons to it. We can just kick it right out. And so this next step, we're going right to the collapse of the tetrahedral intermediate. That negative charge is going to come down and kick out the chlorine. And now we're going to have the double bond to the oxygen back, but instead of the chlorine in that position, we're going to have the NH2. So that one ended up kind of coming down from there. So that's the same NH2 there. We're going to have chlorine as well. And that's why sometimes these neutral conditions, we kind of mentioned that we can have a weak base. The NH3 itself is a weak base, but sometimes depending on what the nucleophile is, a weak base will be paired with it, and that's just because this chlorine can go start to grab these H's if you don't have anything that's a weak base. The chlorine will do it itself, and you'll start to get HCl buildup, and that can really negatively affect some of the functional groups you might have in the molecule and things like that. And so sometimes you'll see this with weak bases as well. In this case, we just kind of had our pi electrophile and our nucleophile, and then that last step was the collapse of the tetrahedral intermediate. We see that this is way shorter than the acidic conditions mechanism. Those two steps are showing up again, so that nucleophile attack and the collapse of the tetrahedral intermediate. We need those because of what we're trying to do in the reaction, substituting out this group for the nucleophile. We need to get that group onto the molecule and then get this group off of the molecule. And so those two steps are going to be the same in all of our mechanisms. The thing that changed with this one, we did still have one proton transfer, and that was right after that nucleophile attacked because we were dealing with two neutral molecules and we got this charged molecule. We do need to make sure that we're making it back to neutral for the end. And so that's why we just had that one proton transfer, but those two other steps are both there.